Hello and welcome everyone to the first video in the operational amplifiers, or shortly named as op amps. In today's video we'll go through the basic definitions and main operation of the operational amplifier device, which can be shown as a two input terminal device, V plus and V minus, to the plus and minus input terminals, and one output voltage VO, and some gain for this op amp is called A.
Okay, so the operational amplifier from both words. The first word is operational, should mean thing, and the second word is amplifier. Let's start first with this word. The amplifier means there is an active element in the circuit. This active element now will work as something will give gains to some voltage or some current inside the circuit, which is different operations that happen before we throw the passive elements like the resistance, capacitors, or coils. So simply we can express this relationship as some linear relationship between the output voltage and the input voltage. We can add some scalar here, which is A. The scalar represents the gain. This gain, for sure, from its meaning, something greater than or equal to 1. The other word, which is the operational, it was first meant to express some mathematical operation. This basic mathematical operation using this operational amplifier was addition, subtraction, integration, derivative. So all of these mathematical operations could consider be some basic operations of the operational amplifier, or simply the op amps.
This operational amplifier is nothing but three-terminal device, the V plus and V minus, and the output terminal V naught. So if we have the input terminal V plus and V minus with difference voltage Vn, and we have a gain inside this amplifier called A, and we have our output voltage V naught, there is some relationship between this output voltage and the input differential voltage Vn in black. What happened inside this symbolic triangle? It's many transistors connected with some resistors with few capacitors to have this kind of operation at the end. So this is just like a black box. And this triangle here, all these devices, all these elements connected together, they have a voltage source connected with plus VCC, and the other negative voltage source, or maybe the ground, we can call it VEE. This one here can be modeled into like a very simplified model. This model just through the input terminals, there is some input resistance Rn between the two input terminals V plus and V minus. On the other side, V output has some kind of output resistance Ro connected to a voltage source, which is here a voltage control voltage source, equal some gain related to this amplifier with Vn. So here we can see from this operations, this Vn equal V plus minus V minus, here, this relationship. For some typical values in the op amp ICs, the integrated circuits, you can Google any data sheet of these op amps. The typical values for this symbols here, the input resistance between 10 power 5, 10 power 7 ohms, some hundreds to few mega ohms. The output resistance of this operational amplifier, it's a very low resistance, something in terms of tens to few hundreds of ohms. When we say like a small output resistance, this is compared with the other input resistance. The voltage gain of this operational amplifier, it's a very high voltage gain. something in the range 10 power 5, 10 power 7. And this model here, as we can see in green, this is called the model for the non-ideal op-amp. So here, let's go again with what's called the ideal op-amp. So here we have the operational amplifier model. We have the plus voltage and the minus voltage for the input terminals. We have Rn here goes to infinity, it means we have an open circuit. And we have the output voltage here, R0 goes to 0, it means there is some short circuit here. So here if we also consider the voltage control voltage source, A times Vn, this A goes to infinite, and we have this Vn here, the difference between the V plus and V minus. If A goes to infinite, so Vn has to goes to 0, so this means V plus minus V minus, this difference has to be 0. This interesting result will lead us to V plus has to be equal V minus. So if we have any voltage at one of both terminals equal to some specific voltage V, the other terminal should have the same voltage approximately, or in the ideal case should have the same voltage exactly V. The other interesting result, if we have open circuit here, it means anything connected here will some current will flow here, but here will have some open circuit, means this I will be 0 and this I will be 0. Means both input currents at the input terminals will be zeros. Regarding the I/O, the output current, this output current here we have A times Vn equals some specific value, so there is some voltage here. Depends on which value here in the load at the end connected to this op-amp, there will be some current I/O, but generally don't forget it's not equal to 0, it's some values depending on the load here, and this is what's called the ideal model for the op-amp.
Some like basic examples just to discuss this thing. We have some basic operation for this operational amplifier. One of the most interesting usage for this interesting device, which is called a voltage buffer or the voltage follower. So what do we mean with voltage buffer or voltage follower? So the buffer or the voltage follower, it's some specific connection for the input and output terminals of this op-amps. You have the same 3 input and output terminals, and this input terminals connected here in such a way the V output is connected to the negative input of the differential input of the operational amplifier. So this is VO, this is our V minus, and this is V plus. If we have input voltage here, Vn, so if we deal with this as an ideal amplifier, it goes first with the ideal assumptions, means V plus equal V minus, and also the current here and the current here has to be 0. So I equal to 0, I equal to 0. And then let's continue with the current, the same branch. So again, this whole current also 0. It means at the end this point and this point has the same voltage. So both points are equal in the voltage here. and V plus already has some specific input voltage. So after substitution, V plus here is equal to our input voltage, our source. V minus in the specific design equal to the output voltage VO. It gave you the relation here, V out over Vn equal to 1. This is some interesting usage of this device. One of the basic operation used in all the analog and digital circuits, which here there is some unity gain, and the voltage at the input terminal just transfer to the output terminals without loss or without gain. But actually there is a big advantage behind this operation. So this is called the unity buffer. To go through this, how this works, this buffer, let's draw a very simple circuit. I have a voltage source here. This voltage source here is 10 volt. I have a resistance here is 10k, and we have a load resistance. This load resistance here, all connected here to the ground, this RL equal to 1k. If we are connecting this circuit in such way, direct connection, and we want to compute this voltage VL across this load resistance, it's such VL, it's a voltage divider, it's equal to the whole voltage 10 multiplied by this 1k divided over the 10k plus 1k, which is actually 10 over 11 volt. So what happens if this RL becomes 10k? And another way, what happens if it goes to be 100k? So now let's go first with the first one here. If we have RL equal 10k, means VL will equal 10 multiply 10 over 20,
and this now will equal 5 volt. So regarding the other value for the RL, here RL equal 100k, so VL will be equal this 10 volt multiplied by 100 divided 100 plus 10, which is equal 100 over 11 volt. So this one we can compare all these values. We have 1k, we got almost 0.9 volt at VL at the output. If it's 10k, we got 5 volt. If the value of RL goes to 100k, VL goes to almost 9 point something volt. So this means this value of the VL will be dependent on the value of the load. In some circumstances, if your load resistance is changing, this VL will change as well, and this something is not recommended in designing the circuits. If we need to get this voltage constant, to get this value independent of the load resistance, we have to figure something else, and this will be shown using our buffer circuit.
Let us use the same circuit. I have here the same voltage source, connect the same ground. We have this resistance again, the 10k. We have this one 10 volt, and here we will make the same connection of the unity buffer. We have here our plus, our minus, and connected between the input terminal and the output terminal. and connect this output terminal to our RL. This is again the VO. Returning back, this VN, if we have this configuration of the unity buffer, it means unity, it means 1. So VO over VN equal to 1. It means the voltage here it will be the same voltage here. Nothing will be depending on the value of R. Mathematically, let's solve this one. First, the most interesting thing you will notice, the current will go through this one. It will be the input here, but for the ideal case, the current I will be equal to 0. It's the input current for the ideal operational amplifier. So in the ideal case, no current, plus V plus equal to V minus with this feedback circuit. Call this later. Talk about this later. Right now, it means the Vn, which is equal the source 10 volt minus I times 10k resistance. This one now is 0, which gave us at the end the Vn is equal 10 volt. The interesting part, V out equal Vn. This V out, it's nothing but the VL. So this equal to VL. From the above value, this will be equal 10 volt. So where is RL in this situation? RL could be changed to be increased or to be decreased. It doesn't matter. Any change for the RL, the voltage across this resistance will be the same. So here it comes to our intention right now. This load voltage, it will be always the same source if we called this one Vs. Any value for RL, any value for the same RS for the simple design, just the voltage here will be translated to the other part of the circuit. What's the benefits behind this? We translated the voltage without any distortion, without any losses in resistance or any other parts of the circuit. And the most beneficial part, it won't depend on the value of RL. So you can change the load, or the load can be changed in any ways. At the end, the load voltage will remain the same as what at the input of this point here, as what happened previously. Just to our knowledge, when I mentioned we have this one, this is some RS and this is Vs, the circuit actually is not as simple as you can notice just the resistance and the voltage source. This could be, as we know from Thevenin circuit, we have this black box, we have many resistance, we have many sources, and just we have two terminals. All these terminals, all of these sources and resistances, all these circuit can be translated into just between the same two terminals here. just one resistance, which is our Thevenin, and one source, which is V Thevenin. So this simple example, it's not actually a simple one, it's a simplified example. So this circuit can be a representative for any complicated circuit you can imagine. Just at the end, this complicated circuit can be approximated or simplified or modeled as just one source and one resistance. If you want to deliver a specific value for your load, just add the unity buffer here. In this way, just the voltage at this point will be translated to the other point on the other side without any losses due to the resistances before or resistance after. This is the main usage of this operational amplifier as a buffer. So now you have did something so beneficial. You have isolated the input circuit from your output circuit. So now what happened in the other left hand side, it won't be influenced by what happened in the output part of your circuit. This is the main definition of the circuit buffer. To wrap up these few things in our video, just we have a model for this operational amplifier, V plus, V minus, and this resistance Rn. The other side you have output resistance and voltage control voltage source. This is the output terminal. This could be considered as this symbol here. This plus terminal, this is minus terminal for the inputs, and this is your output here. This value for this voltage source, again, it's A times Vn. Vn, it's nothing but the difference between both of them. If we are speaking about the ideal case for the op amp, so we have first no input current this way. So here this I and this I, both of them are equal to 0. This is at the input terminals. Again, V plus equal V minus, and this came from the very high gain. A tends to infinity, so your input voltage should goes to 0. So both of them will give you the ideal amplifier. This way, plus, minus, V naught, and this V plus, this is V minus. If you have voltage here V, this one be translated here or transferred here to be the same V, and this output here will be connected to any other circuit or having some feedback. It means the output voltage or the output current again will be sensed. You can see from this way you have a connection again from, as the output will give it feedback again for the input. It will rotate it around. So output terminal will go to one of these input terminals. this is here, which is called the feedback. The last thing we talked about, this one is one of the basic operation of the operational amplifier. We have connecting the minus terminal of the input with the output voltage. This is VO, this V plus, this V minus, and here this one is connected to anything, so just at this point the voltage is Vn. We said this is called the unity buffer, with the relation at the end with this V out will be Vn. And this will be the end of our class today, and thanks for your attention, thanks for your time.